Now let's write the recursive version of our delete at index function. So it's the same function we wrote in the previous video, but we're going to write it recursively this time. It takes the head pointer for a list, which it may modify because I may be removing the very first element. It takes an index, and the goal of the function is that when the function is over, the element at that index of the list, as the list currently stands, has been removed from the list, and the value that was stored in that node has been returned. And so that may modify any part of the list, including the head pointer itself, and that's why the head pointer can be modified. And as usual, my ulterior motive is to show how, for a recursive structure like this, we end up with actually a really elegant solution. Okay, so how do I delete from a specific index recursively? And I have a couple of different diagrams here I want to work with. First, as in the previous case, we observe that if the head pointer is equal to null, then there is no index that makes any sense. So you can't delete anything if the list is empty. And so it says if you can't delete anything, then throw an exception. So if the pointer is a null pointer, then we're already done. So I'm going to throw a runtime error, or whoops, I'm going to throw an out of range exception. And then I will, let's see, throw std out of range. I think in the previous video it was index out of range. Not that the text makes too much of a difference. All right, so in this case, at this point, the list has at least one node. All right, so what can we do to handle this recursively? So as usual, we want to leverage that idea that we can interpret a list as being, well, if a list has one node, there's at least one node followed by the rest. So the question is, how can we sort of hack away at this? How can we take a bite out of the problem? Well, I suppose it comes down to whether the thing we're deleting is at index 0 or not. If it's in index 0, we're deleting the current element. If it's not, then maybe I can have recursion help me with that. So I suppose I'll begin by saying, well, look, if the index equals 0, then I'm deleting the element that is referred to by the head pointer. So I'm deleting the very first element of the list. This is actually something we did in the previous video. So we had a special case for deleting the very first element of the list. So I'm going to do the same thing here. So I'll make a pointer to that element that I'm about to delete. We'll call it delete node. And I'm just rewriting the same code in that special case at the beginning of the iterative solution. The delete node is the head pointer. I'm going to set the head pointer to be delete node arrow next. And so again, conceptually, what we're doing here is we're saying, well, this is the thing I'm deleting. And then I suppose here is my head pointer. I just want to redirect the head pointer to point to the very next thing, the thing after what I'm deleting. And then I want to return the element that was stored in the node I deleted. And remember that unlike a lot of other cases, because we're using smart pointers, we don't have to worry about things like deallocating the node. So return delete node arrow element. Okay, that's it. That is how I delete the element at index 0. And the point that I want to make here is basically that everything else ends up being the recursive case. If I'm not deleting index 0, I'm deleting something else. And I'll try and break it down like this. So suppose I have this list here, and I've drawn the indices for this list here. So in this case, if I give you a pointer to the 6, then from your point of view, index 0 is the 6, index 1 is the 10, index 2 is the 17. And we already saw, if you want to delete index 0, then I can just splice that out. That's what this if statement does. If I get down to line 79, then I am not deleting index 0. Okay, I don't think we write code in the first person. We are not deleting index 0. It's quite respectable in math and computer science to use the royal we. We are not deleting index 0. So if I handed you a list beginning with this node here, from your point of view, here is index 0, here is index 1, here is index 2, but you're not deleting index 0. You're deleting something in this list. Who knows what it is? Index 1, index 100, whatever. In this smaller list, what are the indices? Well, I don't know. This is index 0, this is index 1. In fact, if I start one element later, the indices of this smaller list have all just been shifted down by 1. What was index 1 in my big list is index 0 in my small list. And what I want to do now is delete something from this smaller list. I'm not deleting the 6. I'm not deleting the very first element. So I can recursively think, hey, I'm deleting from this smaller list. If only there were a function I could... Okay, so we're past that point. It's this function. I can call delete at index. So I call delete at index. Delete the element at index. I'm going to want to return its return value. So I call deleted index. I say start at the list beginning at head arrow next. And what index do I want to delete? Well, if you wanted to delete index 1 of the big list, you then want to delete index 0 of the small list. If you wanted to delete index 2 of the big list, you want to delete index 1 of the small list. In other words, you want to delete index or IDX minus 1. And then that's it. I have a way of deleting the first element. I have a way of delegating the deletion to a different function call if I'm not deleting the first element, and I know how to handle an empty list. And I think that's everything I have to do. And then when I make the recursive call to delete at that index, I return its return value because that's the element that I deleted. All right, it seems almost creepy. It seems like it shouldn't be this easy. I think this is even a more stark example than the filter case. The filter case, we knew that was a sort of a tough function. There was a lot going on there. But here, I have managed to turn this into, I basically was able to turn over the entire set of work just by subtracting 1 from an index. So we'll try running it and just hope that it doesn't crash. And it doesn't. And just like in the last video, I will go over the full testing sequence. So here is the original list. We can see, I'll scroll to main to show it off, but hopefully we can agree it's the same list as before. 6, 10, 17, 111, 187, 116. There it is, it's being printed out. I delete the element in index 0. So I get the 6. That looks good. And then index 0, what was previously index 0, is now gone. Okay, so now the head pointer points to the 10. And I have to adjust all of the indices to compensate. Okay, so the 10 is index 0 now, 17 is at index 1, 111 is index 2, 187 is index 3, 116 is index 4. Now I deleted index 3. Well, I print the list out, and it does look like I'm correct there. I deleted index 3. Index 3 is the 187. Sure enough, I return 187. This is definitely deep into our recursive case. And then I've spliced that out of the list, so we'll just delete the node. So we end up with this. And so now the indexing is changed again. So 116 is now at index 3. I print the list out. Yep, that looks good. I now deleted index 2. That would be this thing. I do see that I deleted the value 111. When I've spliced that out of the list, then we end up chaining together the 17 directly to the 116. I print the list out, and there it is. And so I hope that the last sequence of videos, all of the different iterative and recursive solutions that we've written, has been enough to prove the elegance of recursion. This, I think, is amazing.